Hello and welcome to our next set of college algebra notes. We are on Unit 2, Outcome 7. So we are kind of getting into working with larger polynomials and trying to solve them, which is a way of saying find all the zeros, find all the numbers that would make them zeros. To do that, to work with these larger polynomials, we will want to factor them, break them down. We saw that when we were working with quadratics, factoring was the easiest method that we could use. So we'll try and use factoring as much as possible. But it's a lot harder to factor a big polynomial. So we're going to actually use some different techniques for factoring. One of the big techniques is to divide. Because remember, factoring is writing something as a multiplication. And so when you divide stuff apart, you can actually find out what multiplies to make that thing. So that's what we're going to do here. So first, before we get into solving these big polynomials, we're going to talk about how to do division. Now, with polynomials, you can do traditional long division, just like you did with numbers back in grade school. So that's what we'll start off with. We'll start off and show you a couple of problems where we're going to use polynomial long division. So remember long division, you have your box where you're going to put the number you're trying to divide. So I'm going to put this x squared plus 8x plus 15. It's going to go inside that box, and then to the left of it, we write the number that we're going to divide by. And so we're dividing by x plus 5. So, of course, top number is being divided by the bottom, so that's how we write this. And when you did long division back in grade school, you always thought, okay, how many times does this fit into the first part of the number? And then you would multiply that and subtract that. So it gets a little more awkward to do that here, because trying to figure out how many times x plus 5 fits into x squared is not so easy. But what you can do to make it simpler is you could just think about what would I have multiplied x by to get x squared. So if I want to make this x into an x squared, what would I multiply by? And the trick is you just multiply by x, because x times x would give me x squared. So I'm going to take this expression I'm dividing by, I'm going to multiply by x, and that's what I'm going to subtract. So I do x times x, I get x squared. I do x times 5, I get 5x. And I'm going to subtract that whole thing. So I'm going to take that whole thing and subtract it. Okay, so I take x squared and I subtract x squared. I get nothing, so that part's gone. I get 8x, subtract 5x, I end up with 3x. Remember, you're subtracting the whole thing. Okay, when you did long division in grade school, you'd do some division, and then you'd a lot of times have to bring more down so you could continue the problem. The same thing happens here. To finish the problem, I'm going to bring this 15 down so I have more stuff to work with. And then I'm going to think again, what would I multiply this by, specifically the x, to get this 3x. And so I say, okay, well, 3 times x would give me 3x. So I'm going to put a positive 3, because I would multiply 3 times x to get the 3x, and 3 times 5 to get 15. And again, I'm going to subtract that whole thing, subtracting all of that. Subtract 3x, there's nothing. 15 minus 15, there's nothing. And this is one of those cases where there's no remainder. There's no leftovers, right? We got 0 at the end, so there's no leftovers, no remainder. That's not always true. We'll see some problems with remainders today. Just like when you do division normally, you can have division, you can have remainder. But that's the idea of division. This is called polynomial long division, because we do it just like traditional long division for small numbers. We write down what we're dividing by and what we're dividing by, and then our answer is up here in the box. So our answer for this problem would be x plus 3. That is our answer. That is the quotient. That's what you get if you divide that polynomial by that polynomial. Now, another way of thinking about this is the fact that, remember, division and multiplication, they're kind of opposites. They have those fact families you probably learned about in grade school. That if I can take a big polynomial divided by x plus 5 and get x plus 3, that those two small parts, the x plus 3 and the x plus 5, multiply back together to give me the original polynomial. So we actually know that x squared plus 8x plus 15 is equal to x plus 5 times x plus 3. So another way of thinking about this is that we actually factored that original bigger polynomial. When you divide, and it divides evenly, there's no remainder, you've actually factored the polynomial. And we'll get more into this later, because this is actually probably one of the most important things we're doing with the division, is we're going to divide and use that as a method for factoring. Because if I have a big polynomial and I can't solve it until it's factored, I'll factor it and then solve the parts. The smaller parts, it'll be easier to work with. So like here, it's a lot easier to solve x plus 5 equals 0 or x plus 3 equals 0 than it is to solve x squared plus 8x plus 15. Of course, that one is a quadratic, and we can factor or use the formula, stuff like that, to solve it. But we'll do this for bigger polynomials. In fact, the next problem we have Here's an example of this. Let's try the next one. So we're going to do division again. Now you can see we're dividing with a much bigger polynomial. So we have this big polynomial, x to the fourth plus x to the third, that's 8x squared plus 4x minus 48, all of that. And we're going to divide it by this x squared plus x minus 12. So we're dividing that big polynomial by that quadratic polynomial, that degree 2. And again, we're going to think about the first term here, this x squared, and think about what I have to multiply to get x to the fourth. Well, to get x squared to become x to the fourth, you just multiply it by another x squared, right? X squared times x squared, you add the powers, you get x to the fourth. So that's what I'm going to multiply by. So I'm going to take this entire expression and multiply it by x squared, and that's what I'm going to subtract. So I'm going to take away, I'm going to do x squared times x squared gives me x to the fourth. X squared times x gives me x to the third, and that's a positive x to the third, right? Positive. X squared times negative 12x, 12 gives me a negative 12x squared. And again, I'm going to subtract all of that. So all that stuff I'm going to subtract. So I take x to the fourth and subtract x to the fourth, it's gone. So there's nothing there. X cubed, subtract x cubed, and it's gone. I do negative 8 minus 12, negative 12. So minus a negative, remember you actually add, because the double negative is adding. So negative 8 plus 12 ends up with a positive 4. So we get positive 4x squared. Okay, that's just the first step. Just like before, we're going to bring stuff down. Since this one has 3 parts, we only have 1 down here, I'm going to bring down both of these parts, because I want to have as many parts down here as I do over here. So I got the 4x, positive. I got the negative 48. Now I'm ready to think about what do I multiply this x squared by to get 4x squared. Well, all I have to do is multiply by 4. I'm going to put plus 4 here. So I'm going to multiply that by 4. So 4 times x squared gives me 4x squared. 4 times x gives me 4x. And 4 times negative 12 gives me a negative 48. I picked 2 that come out nicely because, again, this one, when I subtract, I get 0, 0, 0. Again, this one has 0 remainder. Again, that doesn't always happen. I picked a couple that do just to start us off. So this shows us what we've seen right here. The big thing is that this big polynomial, this x to the fourth plus x cubed minus 8x squared plus 4x minus 48, this whole polynomial is equal to the product of the number we divide, the polynomial divided by, and the answer we got. So you can get that by taking x squared plus x minus 12 and x squared plus 4 and multiplying those together gives you this big polynomial. Now why is that a big deal? Well, if I had just given you this original polynomial and said, here, set it equal to 0 and solve, find all the answers, find all the zeros, you would have probably been at a loss, like, oh, I don't know what to do. But if I break it up into these two polynomials, and I give you these two separately, say, okay, here, take this one, set it equal to 0 and solve it. Take this one, set it equal to 0 and then solve it. It's not a big deal because they're quadratics. So you can just use the quadratic formula because that's what the quadratic formula is for these x squared polynomials. In fact, this one you could even use the square root property where you just get x squared by itself and square root both sides. So they're not that bad. I think you can factor that one too. So by breaking it up into smaller polynomials, you make it solvable. You make it so, okay, now I can solve it. This is probably the easiest way to solve these really big polynomials is you divide out a smaller polynomial and then you take the answer and, solve that. What you divided out and the answer that you got, and you do those. And again, the answer to this division problem, though, is just the x squared plus 4, right? That's the answer to the division problem. So if I'm just asking you to divide, that's it, you're done, x squared plus 4. But as we go, we're moving towards using division as a way to break up these big polynomials into smaller ones and solve. Now, I'll tell you, you don't really need to use polynomial long division to divide. There's actually another method. It's called synthetic division. It's kind of a briefer, easier, faster way to divide, but it only works for certain situations. So a problem like this one, you couldn't use synthetic division on. Problem like the first one, you could. The difference is when we're dividing by just x plus a number, versus this one, we're dividing by a whole quadratic. So synthetic division only works if you're dividing by x plus a number or x minus a number, a single little linear term like that. Since that's the primary way we break up the big polynomials, it actually is still really useful. It's really useful to just do this kind of division all the time. So we'll do that with synthetic division. We won't actually see a lot of division like this. This can happen, but it's not something that's going to be super useful for us, so we're not going to see it. And I do like to show it, because if you're going to go on and take, calculus course, stuff like that, you'll probably see some polynomial long division show up here or there throughout your calculus courses. So at least I'm kind of giving you a preview of that. But synthetic division is going to be what's going to be useful for us for this semester. So I'm not really worried about you learning long division. So the stuff I showed you on the first page, you don't need to use it. I think some of the homework questions in my math lab will say use polynomial long division, but most of the time you can get away with synthetic division. Again, as long as you're dividing by something like this with like x plus number or x minus number. If you divide by something bigger like this, then you can't. But I don't think they give you any problems like that. Okay, so let's show you synthetic division. Like I said, it's going to be what you use more. It's the easier, probably faster way. What it really is someone kind of took the idea of long division and said, okay, if I can make a little tweak, a few tweaks to this, pull some stuff out, simplify some stuff, can I make this a lot easier to do? And then they made up this method. And so this method is based on long division, but it should be a lot easier. So the first thing you do when you're doing synthetic division is you look at what you're dividing by. So I'm dividing by x minus 2. And you take the number part of that. We're going to drop the x's primarily because that just makes life easier if you don't have to worry about writing a whole bunch of x's. So we're going to take just the number part of that. We're going to put in a box up here, but we're going to change the sign. So instead of doing a minus 2, we're going to do a plus 2. Now, why do we switch the sign? Well, by switching the sign, instead of having to subtract to do this problem, we're going to be able to add to do the problem. And I think most of us will agree that it's a little bit easier to add numbers than it is to subtract numbers. So that's something you'll see. We're going to switch the sign. Every time we do this, we're going to switch the sign. And that way we can add when we do the problem. Okay, the next thing I do, like I said, I'm going to drop the x's. So I'm going to look at these numbers up here, and I'm going to write down just the coefficients. I'm going to ignore the x's. So like in front of the x squared, there's a default 1, so put a 1 there. In front of the x, there's a 3, so put a 3 there, the positive 3, right? So it's sometimes good to think about the sign there. Those are the positive. The 10 is a negative, so we'll put a minus 10. So I wrote down those coefficients, the number parts. Again, I'm dropping the x's because now when we're doing synthetic division, we don't have to worry about the x's while we do it. That's kind of the nice thing. Okay, so I'm going to leave myself room for a line of numbers. I'm going to put a bar underneath that. And then underneath the last number, I'm going to put a little box. Because in that box is where your remainder shows up. I always like to label it with a little r, so I remember that's where my remainder goes. A lot of people do this, they might not put a box there, but I like to have the box because that helps me remember that's the remainder. I also like to write that I'm going to add, because it said I don't want to subtract, I'm going to add, and I'm going to multiply. Because we saw when we did long division, we always had to multiply, right? You take the stuff that you got for your answer and multiply it to get the stuff you're subtracting. So we're going to end up multiplying and we're going to end up adding. All this is coming from long division. But again, I took out all the x's, so we're not going to see any x's while we do it. And it's just going to go a little bit faster than when we had to do long division. So first thing I'm going to do, I'm going to add 1 plus nothing, because there's nothing here to add, right? So we're going to just bring that down. So the first part of my answer is going to be a 1. Then you take the part of your answer and you multiply it times what's in this top left box, the thing we're dividing by. So I'm going to do 1 times 2, I'm going to get a 2 right here. Next thing I'm going to do, I'm going to add the 3 and the 2, and I get a 5 down here. And then I do my multiplication again. So I do 5 times 2, and I get a 10 in the next column. I add again, negative 10 plus 10, and I get 0. And because I have 0 remainder, this means they do divide evenly again. So this is one of those again where they divide evenly. We'll get to one where they don't here in a second. Okay. Now, I took the x's out. The last thing I have to do is actually go back and put the x's back in. Remainder never gets an x. It's the leftovers. Why would you give it an x? That's silly. The 5 also doesn't get an x, because you'll notice that all of these polynomials start with a plain number term. The 0 doesn't count because it's the remainder, it's leftovers. So the 5 is the plain number term. We call it the constant term. So that's the constant term. Then the 1 will get the x. So we start with, after the constant, we have just the plain x terms. So the 1 is going to get an x. And then I'm done, right? There's no more numbers. If you had more numbers, if you start with a bigger polynomial, you might have more numbers. You just keep going, right? You have x, x squared, x cubed, so on and so forth. It all depends on how big you start with. Since I only started with a quadratic, which isn't very big, I only ended up with 2 numbers at the end. And so that's why I only had 2 parts. So my answer to this is this expression right here. My answer is x plus 5. That's what you get when you divide those 2 polynomials. Because 1x is just x, and there's the 5. I don't have a remainder, so I don't have to worry about it. I can just ignore it because there's no remainder. Again, this is another way of saying you can take x squared plus 3x minus 10, and you could factor it into x minus 2 and x plus 5. Those two things will multiply together to give you that original quadratic. We know that because when we divided, it came out evenly. And so, think about the number 6. If you take 6, you divide it by 2, and you end up with 3 for your answer. We can always go backwards, right? You could take the 3 and the 2, multiply them back together, and get the original 6. It's the same idea. I took this, divided by that, and got that for my answer. So if I go backwards, this times that should give me the original thing that I started with. So I'm factoring. So that's how it factors. Now, of course, with something like this, we could factor that by hand, without using division. But again, we're kind of setting ourselves up for bigger polynomials and being able to factor those. Let's try one with a bigger polynomial. This one I threw in here because I saw it in the homework and I was like, oh, that's a little tricky, so I should probably help you out with this. So they actually put i's in this one. So we're going to try and do this one here. The number we have is I. So when I do synthetic division, I'm going to have to use an I in there. Okay, so let's start off. So synthetic division, we're going to start off with, instead of the positive I, remember we always switch the sign, we put a negative I in the top of the box. Then we write down our coefficients. We start off with the 1 from the x cubed, the 5i from the x squared, the minus 12i from the x, and the minus 11. So again, I'm just writing down the number parts. I'm ignoring the x's, right? I'm just dropping the x's and writing down what's left. Leave a space. My remainder box is here. That's where my remainder is going to go. I'm always adding first and then multiplying. I always like to put the plus at the times just to help myself remember what I'm doing. Okay, 1 plus nothing. So just bring it down. You get 1. 1 times negative I is just negative I, right? 1 times anything, you just keep it the same. 5i minus I is 4i. It's a positive 4i, right? Because there's a positive 5 minus 1 is going to be positive 4. 4i times minus I. So here you got to be careful. Remember that an I times an I is an I squared. And an I squared changes the sign. So instead of negative 4 that I should get, I end up with a positive 4. Because I had negative I times 4i. I times I was I squared. Negative 4 with the I squared gives me a positive 4. Now these ones I can't quite add and get a nice answer, so because this one's i's, this one's real parts, right? 4. So I'm actually going to get plus 4 minus 12i for that part, right? And since there's no I on this part, I can't combine them, so I'm going to leave them separate like this. Okay, I multiply this whole thing times the negative I, so I get negative 4i is going to be part of it. And then the I part, I get negative 12 times I times negative I. So a negative is a positive. 12i squared, but I squared turns it back into a negative. So we had a positive 12, but then the I squared turns it back into a negative 12. So I end up with a negative 12. And you notice I just had to switch sides here because there's the 12 is the real number. I is the measured part. Last part here, I say, okay, take this. I have negative 11 minus 12. That gives me a negative 23 minus 4i. Okay, kind of a mean one, but this is something I saw in the homework, so I definitely want to make sure you saw it. So here you go, they had i's in there. So when we did this, we ended up with something like this. This one, you also have to treat these parts where we have 2 parts. Those are one number, right? So this gets a little fishy, feels a little weird. This is all one number. This is all one number. So when I go back to put my x's back in, skip the remainder. Skip this whole thing as your constant, right? Because I did this problem, got the constant. So I actually put my first x there and put my x squared there. So my answer for this one would actually be x squared plus 4ix plus 4 minus 12i. And then I'd have my remainder. So that'd be my division answer with my remainder would be negative 23 minus 4i. That's what's left over. This one does not divide evenly. When we do division with synthetic division, we always do remainder division because it's easier than trying to think about how do you deal with the remainder. We just put it in a box and say that's the remainder. So we have the division answer. This would be what we call the quotient. It's the answer, and then the remainder is going to be what's left over. So again, trying to help you out with a weird one on the homework. I would never put one like this on the test. It's really beyond what we need for this course. I think they just wanted to make you do some practice on this, or just to make sure you really understand and match the division, the synthetic division setup and stuff. So I wanted to help you out with that homework, but again, don't worry about this for like the test. It won't show up on the test. Okay, let's try a couple more. This one has a little difference that I want to really point out. This is really important. It's something people miss all the time when they're doing this. Is this one is actually missing numbers. So if you look at this, see it's got x to the fourth, x squared, and x. Well, you notice there's no x cubed, right? And normally it's not a big deal because we didn't write polynomials like this. It's not a big deal. But when you go to do synthetic division, you can't skip parts. So you can't skip the x cubed part. And also you notice there's no constant part here either. You can't skip the constant. Now, why would they write them? Well, they didn't write them because if you wrote out this polynomial with the x cubed part, you'd actually see that the x cubed part has a 0 in front of it. And that the constant part of this, the number part of this, is a 0. So you can write it like this because you know that those parts are 0. But when you go to do your synthetic division, you need to include these zeros. I call them filler zeros. So these filler zeros, they're going to fill those spots that are missing, right? The x cubed spot and the constant spot. They are necessary when you do synthetic division. And it's really easy to miss them. You can see how you just write the 1, the -8, and the -32, and you think it's good. And I see that all the time on the test, so I'm warning you now not to do that. But that's what happens is people, they take their -4 and they put a +4 in the top left corner. They grab their 1 from their x to the fourth and they put their -8 and the -32 and they call it good. Well, it doesn't work. And that's why you need the 0. You need the 0 for the x cubed, then the -8, the -32, and you need the 0 for the remainder. If you don't get all of those parts, you're not going to have the right answer at the end. So you need those filler zeros. They have to be in there. So now we can do synthetic division. Our remainder goes down here, and we'll still add and we'll still multiply. If you hadn't put the zeros in, your remainder would be under the 32, and that's the wrong spot. So you'd have the wrong thing for your remainder. So you need these zeros. Okay, first part we always bring down, because 1 plus nothing is still 1. Next time we do 1 times 4, we get 4. 0 plus 4 is 4. 4 times 4 is 16, so I get a 16 here. -8 plus 16 is +8. 4 times 8 is 32. And -32 plus 32 is 0. And then we have 4 times 0 is 0, and 0 plus 0 is 0. So this one actually doesn't have any remainder either. But again, if I didn't do this right, if I ignored these zeros, this wouldn't come out the same because I'd be missing this 0 here and mess things up. Also, when you go to put your x's back in, if you didn't have these extra zeros, you wouldn't have enough x's. Because of this one, you're supposed to skip the remainder, skip the constant. This is supposed to be your x. That's your x squared, and this is your x cubed. And so you're supposed to get a cubic from this, an x cubed. If you didn't have the zeros here, I think you end up with a quadratic, like an x squared, or maybe even just a plain x. You don't get enough terms on the bottom. In fact, that's one way I check to make sure I didn't miss filler zeros, is notice that the answer we get, the power, the degree, is 1 less than the degree of what we started with, right? We started with degree 4, we end up with degree 3. Have you noticed that that happened every time so far? So here we started with degree 3, we ended up with degree 2. Here we started with degree 2, we ended up with degree 1. So that always happens. When you do synthetic division, you always drop the degree by 1. So you can tell you messed up down here if the powers don't match, if it doesn't go down 1 like it should. And that's why I always like to start filling from the right and make sure I stop at the right number. Did it match up? It should be 1 less. It is 1 less, so it did work. Okay, just one more reminder here that we did factor this, right? So by doing this, we figure out that x to the fourth minus 8x squared minus 32x. So this big polynomial with a high degree factors into x minus 4 times x cubed plus 4x squared plus 8x. So as long as we have that 0 remainder, we're factoring it. These two things multiply together to give us this polynomial. And I couldn't do that in the last one. Here I had a remainder left over, so it doesn't work nicely like that. You can't just take this polynomial times x plus I because there was leftovers, and they have to be accounted for. So it only works if it divides evenly, 0 remainder. But if it doesn't have 0 remainder, you did factor it. That's a really powerful thing to do. So let's try one more. I think I have the same problem twice. I don't know why I have it on there twice. That's a big typo. I guess I get to go back and fix my notes. I think I went to add a different problem, and I accidentally forgot to change it. So we're going to skip that one, because that's not the problem we want to do next. We'll go on to the next part. Okay. So there's a couple different uses for division. I already mentioned the one where we're going to factor. We'll get to that here on the bottom half of this page. But the first use is actually you can use division like this, the synthetic division, to evaluate a polynomial. Remember, evaluate a function or polynomial is when you plug a number in for x and get an answer. So we're going to do that. The remainder theorem says that if you want to plug in the number c, if you're substituting for x in your polynomial, the value, what you get when you plug in c, is the same as the remainder if you divide by x minus c. So instead of plugging the number in to get the answer, you can actually find the value that you would get by plugging in by finding the remainder when you divide by x minus c. So for example, they want to find f of negative 2. So we're going to divide by x minus negative 2. Well, we all know that a double negative turns it into a x plus 2. So we're actually going to divide by x plus 2, and the remainder will be the answer. It'll be what you get if you plug in negative 2. So if I went in here and plugged negative 2 in for all these x's, and all the powers of multiplying and adding, subtracting, if I did all that stuff, I'd get the same answers if I just divided by this amount. So we divide by x plus 2. Remember to do that, to do the synthetic division, I take this sign, positive 2, and I switch it to a negative 2. I write down my coefficients. So I got the 4, the 5, the negative 6, and the negative 4. So there's my coefficients. I put my remainder box at the bottom there. So that's where my remainder goes. Got my plus, my times, and then I'm going to go ahead and start. So I'm going to bring this down. So bring down my 4. Multiply negative 2 times 4 gives me negative 8. 5 plus negative 8 gives me a negative 3. Negative 3 times negative 2 gives me a positive 6. Negative 6 plus 6 is 0. Negative 2 times 0 is 0. And negative 4 plus 0 is negative 4. So this remainder is my answer. So by the remainder theorem, the value I get when I do f of negative 2, so f of negative 2 is what I get when I divide by x minus negative 2, so x plus 2. And I got this one for my remainder. So the answer is negative 4. That's my answer. Now, you're like, well, why would you do it that way? Why not just plug it in? Well, it actually, I think, is a little bit faster, especially as the polynomials get bigger. I'll show you the other way, so we can kind of show. This would be a way to check it, I guess, in this problem. Is we could go back and check and see what do you get when you do f of negative 2. So if I plug negative 2 in here, I do 4 times negative 2 cubed plus 5 times negative 2 squared minus 6 times negative 2 minus 4. And then I have to simplify that, right? So I have to do all the simplifying. I have to do negative 2 cubed is negative 8, still times 4. Negative 2 squared is 4. Negative 6 times negative 2 gives me a positive 12, still minus 4. Here I get 4 times negative 8 is negative 32. 5 times 4 is 20. You can combine these two. 12 minus 4 is going to be 8. Okay, I get negative 32 plus 20, which is negative 12, plus 8, which is negative 4. And you got the same answer. And if you prefer, you could do it that way. But I think this is good practice to do our division. And it's good to know that if you're going to plug that number in, the answer is going to be what you get out for a remainder. That's an important fact to know. So that when you do synthetic division, you always know that the number you put up here, if you plug that in, this is the answer you get. So if you get 0 here, you know that that number that you plugged in is actually a 0, a number that makes the polynomial or the function give you 0. So it's a valuable fact to know. So that's the remainder theorem. It says, and I keep saying how this matches here. It's because when you divide by x minus this number, right, x minus number, to do synthetic division, you switch it back again. So if you're doing remainder theorem, specifically if you're doing remainder theorem, then this number and this number will match. When I was dividing, right, when I was dividing by x minus a number or whatever, I'd always switch. But when you're doing remainder theorem, if you switch and switch back, you end up back where you started, right? So that's why these will match, because when I take this and I divide by x minus the number, and then synthetic division switches it back, you end up with these matching. So we'll see that a lot. If we have the number we want to plug in, if we want to try that one number, we'll just put that in the box here. Because dividing by x minus that number, well, you just put that sign on it. Okay, so that's the remainder theorem. Big fact about the remainder theorem. The remainder here is what you get if you plug in that number. That's important to know. Next thing's the factor theorem. And I kind of gave this away. I shouldn't say kind of. I really gave this away, this section, because I talked about it the whole time. This just says that if you f of c equals 0, that's the same as saying there's no remainder, right? So if there's no remainder, then x minus c is a factor. So the thing you're dividing by is a factor. Well, we already knew that, right? That's what I said. When we said that there's no remainder, then it factors, and you can write it as a multiplication. So that's what I was saying there earlier, that if you get 0 remainder, then that thing you divided by is a factor. Okay, so let's try it. We want to check and see if x plus 2 is a factor of this polynomial. So we're going to divide it by x plus 2, see if it's a polynomial, which means, of course, when we divide, we're going to put negative 2 in the box, right? Because you always switch the sign. So this plus 2 that we're dividing by, we're going to turn into a negative 2. Write down our coefficients. So we get 2, negative 3, negative 11, positive 6. Write down our coefficients, put a remainder box. Again, that's what's important. If this is 0, then yes, it's a factor. If this is not 0, it didn't divide evenly, so it's not a factor. That's what we're checking. We're going to add, multiply like always. So I'm going to bring down this first term, because add nothing, you just still have 2. 2 times negative 2 is negative 4. Negative 3 plus negative 4 is negative 7. Negative 2 times negative 7 is positive 14. Negative 11 plus 14 is positive 3. And 3 times negative 2 is negative 6. And 6 plus negative 6 is 0. Okay. It did have 0 remainder, which means yes, x plus 2 is a factor. So another way of saying this is that yes, this big polynomial, it divides evenly by x plus 2. There's no remainder. So again, we can factor it. So 2x cubed minus 3x squared minus 11x plus 6 factors into the x plus 2 we divided by, and the answer we got, right? Because when you divide, the answer is the other part of the factoring. So this one where I put in the x of the 7, the x squared here. So remember, skip the remainder, skip the constant, and then x squared. That is the other part. So 2x squared minus 7x plus 3 is the rest of it. So those two parts multiplied together give us the original polynomial. That's the idea. So if you divide evenly and get 0 remainder, you factored that into two parts. And that's the factor theorem. The factor theorem tells us if you get 0 remainder, you factored it. And now there's the factors, which I said a million times, so hopefully you really got that, because that's the important thing we're really going to use. We're going to use this the whole time, because we like to take these big polynomials, factor them into smaller polynomials, and then these we can solve. You know, x plus 2 just said equals 0. It's easy to solve. This other one, we can throw it in the quadratic formula. It'll solve really easily. A lot easier than solving the cubic. There is a formula for cubic polynomials. I did have to do it in a class one time. It's awful. The formula has like multiple versions. It's really long. It's a pain in the butt. You don't want to do it. You thought the quadratic formula was bad when we could have factored. The cubic formula is a million times worse. So if you can factor, that's the way to go. And most of the time you can figure out how to factor. So that's what we're going to do. We're going to factor as much as possible. We're going to ignore the cubic formula because it is not fun to work with. We just don't want to have to deal with that. It is not a nice formula. So instead, we'll do this. We'll divide by something that factors that 0 remainder, and that will factor it. And then we'll just solve what's left. And that's how we'll solve these. So we get there. That'll be most of what outcomes 8 is about, is solving these polynomials using that factor theorem like we're doing. So that's actually what we're going to do on this next one. So they gave us a big polynomial, cubic, degree 3, and they want us to use the factor theorem to find all the solutions. So when they say all the solutions, what they're meaning is set it equal to 0 and solve. That's what they're calling the solutions. Solutions are all the zeros. So the solutions are zeros. So when they want you to solve this polynomial, they're saying set it equal to 0 and figure out what the answer is. Solve it. So because it's equal to 0, we can use the factoring method, where if we factor this, we can settle the parts equal to 0. Now, here's the question, though. What do I divide by? They didn't tell me anything to divide by, right? They just gave me the polynomial. So in the previous problems, they said, oh, divide by this number. Here's your factor, or here's the number to plug in. Use that. They didn't tell me anything. Now, if you go to the homework, and you use the help me solve this, they have the most terrible idea on how to deal with that. They say, guess random numbers, which is just bull crap. I hate that. I wish they didn't say that in the book. That's not the way to do this. Yes, you could sit there and guess random numbers, and I've had people do that on the test before, and sometimes eventually they find one that works, but it's a lot of work. I usually see a whole page of tries until they find one that works. This is not a good method. Instead, notice the fact that if the whole thing is equal to 0, that means that the result, or the y value is 0. Now, polynomials can graph, right? All functions can graph. And we know that if you're graphing and the y value is 0, you're in the middle up and down, which means you're on the x-axis. If you're on the x-axis, you are in x-intercept. So the trick here is to note that when you're looking to make it equal 0, you're actually looking for real zeros or x-intercepts. We said that a bunch in the last section, right? That the real zeros are actually x-intercepts. So we're going to graph to find the x-intercepts because x-intercepts are real zeros. So instead of guess and check like the book says, which is, like I said, it's just not the way to do it. It's ridiculous. Instead, we're going to graph this. Make it for my graph is ready. Okay, so I got 2x to the third minus 5x squared plus x and plus 2. Okay, so I typed it in. Hopefully I got it exactly the way they had it. I'm going to hit graph. I'm going to look for x-intercepts. X-intercepts will be solutions. And I see 3 of them, which is great because this one's degree 3, and we learned last time that degree 3 has at most 3 zeros. So we actually can see all the zeros on this graph. So I can actually just hit my trace key. There's a trace key right there. And you can get close to where it is. And that looks like that one is really close to like -0.5. So if I try -0.5, yep, -0.5. So -1/2 is one of the zeros. That's not a very friendly one. So let's see what the other ones are. That one looks like it's close to 1. So let's type in 1. So just hit 1 and then hit enter. And you can see that 1 is a 0. So 1's a nice easy 0. Looks like 2 might be the next one. Yeah, let's try 2. I'm going to type 2 and hit enter. And there's 2. That's using the trace key, right? So the trace key is how I got a dot on this line. And then you can just type in x values to see if they actually are zeros. Or you can use the second table option, because the table gives you a list of the values. And you can see that there's a 0 at 1, and there's a 0 at 2. So a lot of the easy to find zeros are on the table. So either way you prefer, I don't care which way. You can look at the graph and use the trace key and find the zeros, or you can hit second and the table button and find the zeros that way. But this actually lets us find zeros. Now we can use those zeros as solutions. In fact, we have already found all 3 zeros. So if this was like a multiple choice question or just a homework question you just want to get through real quick, you could just list those 3 numbers. The zeros we found were -1/2, 1, and 2. And those are all 3 zeros. Those are all the solutions. We're done. I am going to warn you that some polynomials have zeros that are either really hard to read off the graph, or they don't show up on the graph at all. Because some of their zeros are going to be imaginary numbers. We don't graph imaginary numbers, so they won't show up. And some of them are going to be square roots. And it's hard to read a square root off a graph. So I would really highly suggest you don't always just use that method of just finding the zeros on the graph and saying that's it. Because it's really easy for a teacher to write a test question where not all the zeros show up on the graph. So if you get really dependent on that, and if you go, oh yeah, I'm just looking at the graph and that's how I find the zeros, you're going to be out of luck when it comes to the test. So this is the way I want you to do it, because this works always, even if they're not all on the graph. So this is the method. The method is to pick one of those zeros. You always have one you can find on the graph, and that's okay. I'll always let you have one on the graph. So we found, let's say x equals 1 is a 0, or a solution. 0 and solution are interchangeable. It makes it equal 0, so it's a solution. So that's a 0. So then we're going to divide out x minus 1. So we're going to divide by x minus 1. Because that'll get rid of that one solution we already found, and then it'll give us something we can solve to find the other solution. So we're going to divide out this. So divide by x minus 1, we're going to put a plus 1 in the box, right? Because we always switch the sign. Notice that this one matches here. So the one we found on the graph, the x-intercept, is what we're dividing by. So you can just do that. You can just pull the 1 off the graph and say that's what I'm going to divide by. Then I take my coefficients, so 2, -5, 1, and 2. I'm going to add, I'm going to multiply. I'm going to bring down this first part, like always. Bring down the 2. 1 times 2 is 2. -5 plus 2 is -3. 1 plus -3 is -2. And 1 plus -2 is -1. And then last, -1 times 1 is -1. 2 plus -1 is, oh, I made a mistake somewhere. Where did I make a mistake? Oh, right here. -3 times 1 is -3. I don't know how I got -2. I should have gotten 0 for me because it's a 0, so that's not how I knew I made a mistake. This should be -2, and 1 times -2 should be -2, and 2 plus -2 should be 0. Sorry about that. I was going too fast, I guess. So, yeah, should have -3 here. So you should get 0. If you don't get 0, then something's wrong, because it is a 0, so the remainder should be 0. So that's how I knew I made a mistake, and I got to go back and fix it. Okay, so the idea is you divide out the x minus 1, divide that out, to factor this, because if it has a zero remainder, we factor it. So we actually broke this polynomial into, so we broke f of x, that polynomial, into the x minus 1, which we already knew was a 0, because that's what we divided out, and then this that was left over, or the answer. So here, if I put my x's back in, this is remainder, constant, x, and x squared. This becomes 2x squared minus 3x minus 2. So that's what you get. Now, we already know the first part. That's going to give us 1 is 0. That's already one of them. This one's going to give us our other two zeros. So this one I'm going to solve. I'm going to set that equals 0. Set 2x squared minus 3x minus 2 equals 0. And then solve that. Now this one's not very nice to factor. You can factor it, but it's not a nice one to factor. I'm just going to use the formula. So let's use that formula. Remember the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac all over 2a. So if I grab the a, b, and c off this guy, I could use that formula. So I get x equals negative b, so negative 3 is a positive 3, plus or minus square root. I get b squared, so I'm going to have negative 3 squared minus 4 times a, which is 2, times c, which is negative 2, all over 2 times a, which again is 2. Okay, let's simplify a little bit. So I get 3 plus or minus, well, negative 3 squared is just 9, so that's 9. 4 times 2 is 8, times 2 is 16, but a double negative makes a positive, so that's 9 plus 16. On the bottom we have 2 times 2, which is 4. Here you get 9 plus 16 is 25, so I get 3 plus or minus root 25 over 4. And root 25 we can do, so we actually get 3 plus or minus 5 over 4. Now remember, when you're doing plus or minus like this, if you can actually do the addition and subtraction, you should. So I'm going to break this up into 3 plus 5 over 4 and 3 minus 5 over 4. So I can do the addition. So that's going to give me my two different answers. So I get 8 over 4, the first one, and I get this one becomes negative 2 over 4. So I get negative 2 over 4, which turns into, if you simplify, 8 over 4 is 2, and negative 2 over 4 is negative 1/2. And those are the other ones we found off the graph. Like I said, because these were all nice whole numbers, fractions, they weren't like roots or imaginary numbers, they all showed up on the graph. So you could find those on the graph. So if you just really need the solutions, this one, graphing, would have got you all three solutions. But this method, I want you to show this method, I want you to do this method, because if any of the solutions are roots, or if any of them are imaginary, this is the only way to get them all. So we're going to do this. We're going to find one of the solutions, find one of the solutions on the graph, divide that one out, take the answer that you get left, typically a quadratic like this, and you usually will end up using the quadratic formula because that's the way to solve it if it's going to give you imaginary answers or square root answers. If it factors nicely, you could factor, but I'm probably not going to give you one like that on the test because the ones that factor nicely will usually be nice whole numbers you could just read off the graph in the first place. So the solutions for this polynomial were the 1 we found, the 2 we found, and the negative 1/2. Those were the three solutions. And we know there's no more, right? We know there's only 3 because we said degree 3 can have at most 3 solutions. And that's what we saw in outcome 6. So that's it for that one. Let's do one more problem and then we'll be done. So one more practice with this. Again, we're going to do this. This one, the problem tells us to use the graph, which is great because now we know that's the way we're supposed to do it. Again, they should have told us to use the graph in the last one because that's the way to do it. Now, back in the day, they had to do it in more fancy, harder methods. But thankfully, now you have a fancy graphing calculator, so you can just do that. That's what most people do nowadays. If they have a polynomial and they want to solve it, you just pull the graph up, find an x-intercept, and there you go. From there, you're kind of home free. Okay. The big difference on this one, though, is that actually it's degree 4. So this degree is higher this time. So we'll see how that changes things a little bit. Okay. First off, we're going to graph it. Let's graph this and see what its graph looks like. So I'm going to put in my x to the 4th, the minus x cubed, x to the 3rd, minus 18x squared, minus 52x, and minus 40. So I'm just typing that polynomial in there. So I typed it in just as it shows. And then we're going to graph it. You can see the zeros when you graph it. So there's 1. Looks like it's pretty close to negative 1. There's another one, looks like it's close to 6 maybe. If I use my trace key and try negative 1, see if that works. Oh, it's not -1. It's actually a little bit past. Oh, that's not very helpful. Did I type that in right? Make sure I typed it in right. X to the fourth minus x cubed minus 18x squared minus 52x. This is looking kind of fishy. 6. Oh. I think something happened with my notes. I must have made a mistake on my notes because that's not supposed to be. Oh, no, that's right. Uh-oh. No. Alright, this is where I cheat and go back to my drawing board because I think I might have messed up my notes because I want a problem that we can solve, and it's looking like I might have accidentally mistyped this one so that we can't. So I'm going to just make sure we don't have a bad problem. Okay. Oh, yeah, that's what it is. There's a typo on this. Sorry. It's supposed to have a plus on the 52. That's why. Okay, let's go back and fix that. So I typed it as I had the wrong thing on here. It's supposed to be a plus. So let's change that to a plus. Okay. So it is possible to write polynomials where graphing won't find any of the solutions, and we're not really going to worry about those. I just won't give you any of those on like the test or anything. That's what happened when I changed that plus to a minus on this one, is you can't solve it using this method we're using because it wouldn't have had any solutions. So sorry about that. That was a typo. Fix the typo. Now when we graph it, it should show up on our graph with actual solutions. Okay, and it looks like the solutions are -5. So if I hit trace key, -5, that's one of the solutions, and 2 is one of the solutions. Like if you do second table, you can find those on the table because there's 2, and then -5 would just be further up, and there's the other one. So that was my bad. Sorry about that. Somehow I just typed that in there wrong, so I had a mistake. I've got a couple things to fix on the set notes. Okay, so from the graph, we found 2 of the solutions. We found that -5 and 2 are zeros or solutions, right? Zeros and solutions, just 2 different names for the same thing. Now, we don't have all of them though, right? This degree 4 can have up to 4 zeros. So we need to keep looking. So what we're going to do is we're going to do like last time. We're going to take, one of these guys and we're going to divide it out so we can solve what's left after we divide it out. So it doesn't matter which one we pick. Let's just start with the positives. I'm going to start with the 2 and do my division. So now I've got my 1x to the 4th, my -1x cubed, my -18x squared, my positive 52x, and my -40. So I'm just going to write it like that. And then I'm going to do my division where I get my remainder down here should be 0 because we know that 2 is a 0. And I'm going to multiply, see what we get. So I get 1, break it down. 1, 2 times 1 is 2. -1 plus 2 is 1. 2 times 1 is 2. -18 plus 2 is -16. 2 times -16 is -32. 52 minus 32 is 20, and 2 times 20 is 40, and yes, when you subtract, you get 0, or add, you get 0. So it does work out, gives me 0 remainder, and again, that shows that yes, 2 is a 0, because we just showed it. If you plug in 2, you get 0, and we can take what's left to find the rest of the zeros. Okay, so skip your 0, skip the remainder, skip the constant, x squared, x cubed, went down 1 like we expected. Now, before we would just take it, throw it in the quadratic formula, but this one's actually a cubic. It's not a quadratic. So when you're doing with degree 4, you can't just do this once and then use the formula. In this case, now we have to solve this cubic. Well, the nice thing is I gave us one that had a second 0, and I'll always do that. If I give you a fourth degree like this, I'll give you one that has at least 2 zeros, because then what you can do is you can take this expression, which is down here, and divide out the other zeros, because they should still be part of it. So we're going to factor it further. So we're going to take it, we're going to do -5 as our division, but instead of going from the original the original polynomial, we're going to start with this polynomial. So we're going to do the 1, the 1, the -16, and the 20 from the cubic, and by dividing out this other 0, we'll only have left in the final answer here just the rest of the zeros, so the ones we haven't found yet. So that's the trick. The higher the degree, the more times you're going to have to do this division part. So if I gave you a degree 5, you'd end up having to do it 3 times before you could hit the quadratic formula. If I gave you a degree 6, you have to do it 4 times before you hit the quadratic formula. But if I give you anything like that, I would always give you one with enough zeros that are on the graph so you could do that. So degree 4 will always have 2 zeros. Degree 5 would always have 3 zeros. I probably won't do any of those to you because that's enough. Degree 4 is high enough for us. But you could expand this. You could keep going. You can use this technique. As long as you can find enough zeros on the graph, you can divide out the ones you need to and then just solve what's left. Okay, we're going to add and multiply like always. We have a remainder here, which we expect to be 0 because we know that negative 5 should be a 0. So bring this down, I get 1. Negative 5 times 1 is negative 5. Add, you get negative 4. Negative 4 times negative 5 is positive 20. Add, you get 4. Negative 5 times 4 is negative 20. And add, you get 0. Hey, that's what we expected, right? We expected to get 0. Go back and add our x's again. So skip the remainder, skip the constant. There's my x. Here's my x squared. And now what I'm dealing with is another quadratic. So again, we're going to go back and we're going to use either factoring or the quadratic formula. This one, I need 2 things that multiply for 4 and add for negative 4. I don't think anything does that, right? Because if I use two 2's, like 2 plus 2 is 4. But in order to get negative 4, I have to have a negative 2 and a negative 2, and they would not then. Oh, that would work. No, I'm making this harder than it is. So we'll use formula or factoring, because if factoring works, that works. So formula or factoring, whichever one works. I'll give you problems where you have to use formula, so you definitely want to be ready for that. But this one, I believe we could factor, right? So if I take this, I break it down, x minus 2 and x minus 2, this is positive 2. Negative 2 times negative 2 is positive 4. So I get positive 4. Negative 2 plus negative 2 is negative 4. So I should get, yeah, okay. So I should get 2 more zeros that are both 2. So I'm going to set that part equals 0, so I have x minus 2 equals 0 twice, right? So that's another 0, so another 0 is x equals 2. Now, so this one had 4 zeros, and 3 of them were 2. Did you catch that? So we divided out one of the 2's. So that was 1 0, that was a 2. We divided out 5, and then when we were done, we still had 2 more 2's. So this polynomial, this actually f of x factors. F of x factors into x minus 2, x plus 5, because of the double negative, x minus 2, and x minus 2. So this would be a case where even though all the zeros were real, it was hard to figure out what all the zeros were because one of them was repeated. You could write this as x minus 2 quantity cubed times x plus 5. And you can see that the only 2 real zeros, the only 2 zeros are really 2 and negative 5, but because this one's multiplicity 3, that's why we got such a big polynomial. So we had 2 zeros, so the zeros, or solutions, are 2 and negative 5, but 2 has multiplicity 3. So that's how that one worked. It was kind of a weird one because we had that multiplicity 3, 0, that 2. That's what happened there. So again, when you're doing this, the idea is you look at your polynomial, graph it, find your zeros there, divide out your zeros. If it's a quartic, degree 4 like this, you'll have to divide out 2 of them and then solve what's left. Whether you use the factoring like I just did, or whether you use the formula, because once you've divided out 2, you'll have a quadratic you can solve with the formula of the factoring. We'll do lots more practice with this in the next section. We're also going to talk a little bit about how to go backwards, how if you have your zeros, you can go back and get the original polynomial. That'll be a part of the next section as well. But this is the big idea, is you can use the graph to find the x-intercepts, divide out the x-intercepts, and then what's left you'll solve a lot of times using the quadratic formula. And that will give you all the different answers for the polynomial. Okay, so that's it for this section. I'll see you on the next set.